determinants and multiplicative inverses of matrices. Last section of chapter 2, y'all. So each square matrix has a determinant. Determinants are only for square matrices. So a 2x3 matrix does not have a determinant. There is no... So the notation for determinant is like absolute value bars. So this does not have a determinant. So NA or DNE does not exist. Whatever. Highly likely to be a trick question on a test or quiz. So the determinant, to denote the determinant, you put the matrix in these like absolute value bars, or you write DET out front. And so you can do this for any square matrix. We're going to talk about it for second order and third order square matrices. Anything higher than that becomes a huge pain to calculate by hand. And if you ever needed to do that in real life for some reason, you would use a calculator or a computer. So the determinant of a square matrix is really easy. You multiply this diagonal, and then you multiply this diagonal, and you subtract them. It's important to do it in that order. Multiply the diagonals and subtract them. That's your determinant. Very easy. If the determinant is not equal to 0, the matrix is invertible. So, if it's equal to 0, not invertible. If it's not equal to 0, it is invertible. Talk about what that means in a second. So, find the value of this matrix, the determinant of this matrix. So you multiply this diagonal, 8 times 6, which is 48. And then you multiply this diagonal, 4 times 7, which is 28. And you subtract them, and that is equal to 20. The value of the determinant is 20. The value of your determinant should be a number. Unless you have variables in your matrix, then it could be a variable. But it should be a single term. Or the sum or difference of terms if there are variables involved. So, let's practice. 2 times 5 is 10. 3 times 7 is 21. 10 minus 21 is negative 11. Yes, your determinant can be negative. That's totally fine. Nothing wrong with that. 6 times negative 3 is negative 18. 4 times negative 1 is negative 4. Remember that we're subtracting, so distribute that negative. We're subtracting a negative. Negative 18 minus negative 4 is going to be negative 18 plus 4, which is negative 14. So the most common mistake people make in terms of determinants is not watching those negatives. Negatives get very tricky here. Keep an eye on them. For C, 0 times 1 is 0. And 0 times negative 1 is also 0. And 0 minus 0 is 0. So A and B are invertible. And C is not invertible. So, for higher order determinants, we mostly use the minor. So the minor of an element of any nth order determinant is a determinant of order n minus 1 that can be found by deleting the row and column containing the element. So one method of evaluating an nth order determinant is expanding the determinant by minors. And so we did this. If you remember back in our section on vectors, we did this. This should look really familiar. So what you do is, right, you take this first element. You're going to use the elements in the first row. You take the element in the first row, and you get rid of the row and the column that it's in, and you take the determinant of the minor, what you get when you delete the row and the column. And then you do it for the next element. You're going to take this one, and you delete this row and delete the column, and so you take the determinant of the remaining 4 elements. And then you're going to do the same thing for the last one. You're going to take this element, you're going to delete the row and the column, and take the determinant of the remaining 4 elements. And then one last important thing, this is a minus, and this is a plus. Always. Now that said, it may switch if your determinant here is negative. Minus a negative becomes plus. But it always starts out as a minus and then a plus. So, remember doing this for vectors, for finding the cross product? So, there's another method. So this is the one that we learned when we were doing vectors, evaluating, expanding the determinant by minors. There's another way. So here's our original matrix. Copy it. Write the exact same matrix next to it. Take these 3 diagonals, and these are going to be the positive ones. And then take these 3 diagonals, and these are going to be the negative ones. So, multiply 3 positive diagonals and 3 negative diagonals. Maybe it would make more sense to make orange be here so that you get each of the top row once. But 3 positive diagonals, 3 negative diagonals. So, you can do whichever method you like. You can do it this way, or you can do it by minors, whatever. Gets you the same answer eventually. So, find the value of the determinant of this matrix. So, we can try it both ways. So, negative 4, watch those negatives, times the determinant of the minor that we get if we cross this row and this column out. So negative 1, 3, 4, negative 3. Minus, we do the same thing for, take this, cross out the row and the column, negative 6 times the determinant of the minor, plus, I think wrong button. Plus, take this last element, cross out the row and the column, and the determinant of the minor. And so this minor, the determinant of this minor is going to be negative, is going to be 3. Negative 1 times negative 3 is 3, minus the other diagonal, which is going to be 12, and that's negative 4, times that determinant. 3 minus 12 is going to be negative 9, times negative 4 is a positive 36. And then we're going to do the second one. This diagonal is negative 15. This diagonal is negative 6. Negative 15 minus negative 6. And then all of this is times that negative 6. So negative 15 plus 6 is negative 9. And this is negative 6. And don't forget that this is a minus. So negative 6 times negative 9 is a positive 54. So minus 54. And then this diagonal, so 2 times this diagonal is 20, and this diagonal is 2. That's going to be 2 times 18, which is 36 again. And this is a plus. So 36 minus 54 plus 36. 36 plus 36 is 72 minus 54 is 18. That's our determinant. Now, method 2, just to show you here. We take the determinant and we're going to write the exact same matrix again here. Write it just like that. Now, our positive diagonals go this way. So negative 4 times negative 1 times negative 3 is going to be negative 12. And then we do this diagonal. Negative 6 times negative 3 times positive 3 times negative 2 is going to be positive 36. And then we take this diagonal. 2 times 5 times 4 is 40. Those are all the pluses. And then we do the negative diagonals. So here's a negative diagonal. So that's going to be minus 4 times 3, which is 12, times negative 4 is negative 48. So that's minus negative 48. Negative 48. So minus a negative 48 here. And then this diagonal, negative 3 times 5 times negative 6 is going to be 90. So that's going to be minus 90. And then negative 2 times 1, negative 1 times 2 is 4. So that's going to be minus 4. Minus 4. And so if we add and subtract all of these, I like to add the positives and then add the negatives. So 36 plus 40 plus 48, right? Because the minus and negative is a plus. So that's 76, 84, 124. And then do the minus 12 minus 90 minus 4 is negative 106. And so 124 minus 106 does equal 18, which is what we got last time. Thank goodness. I was going to be really mad if I messed this one up. Okay, so 2 methods of doing the determinant. This one takes up a little bit less space. but you are more familiar with doing the other method from the vector chapter, so however you want to do it. As long as you get the right answer. Watch those negatives. Alright, so I'll do one of these one way and one of these the other way. So 4 times the determinant of the minor, which is going to be 4 times negative 15 times 7, which is 105. So negative 105 minus negative 10. And then minus 1 times the determinant of the minor, which is 5, negative 1, negative 2, 7, which is 35 minus 2. And then plus 0 times, who cares? Because it's times 0, that's a 0. Who cares what goes in here? Doesn't matter. If we're multiplying by 0, it's 0. So, you can just kind of skip that part. So this is 4 times negative 105 plus 10 is negative 95. And 4 times negative 95 is negative 380. And then this is going to be minus 1 times 33. And so minus 33 is negative 413. Yikes. Hey. You know, it is what it does. For this one, I'm going to try this one doing the other way. So, rewrite your matrix right next to it. Okay? And so then we're going to do the diagonals. So, the positive diagonals, 6 times 3 times 0, which is just going to be 0. And 4 times 3 times negative 9 times 9 is 108. So 4 times 3 times negative 9 is going to be a plus 108. And negative 1 times 0 is also a 0. And then the negative diagonals will go this way. So we have minus 6 times 3 times 0, which is 0. And minus 0 times 4, which is also 0. We'll do that in purple. And then minus negative 9 times 3 times negative 1, which is going to be minus 27. And this should have been a minus because it's plus a negative. All right, plus negative 108. So you end up with these numbers. All right, 0 minus 108 plus 0 minus 0 minus 0 minus 27. And obviously we can ignore the zeros. And so negative 108 minus 27 equals negative 135. The identity matrix of nth order is the square matrix whose elements in the main diagonal from upper left to lower right are 1s, while all other elements are 0s. If a matrix is this, the inverse matrix is defined such that when you multiply the two matrices together, you get the identity matrix. So, you multiply a matrix by its inverse, you get the identity matrix. So, the inverse of a second order matrix, assuming that it is invertible, that the determinant is not equal to 0, then your inverse is going to be 1 over the determinant times this. And so what happens here is the A1, B2, that diagonal switches. And then the B1, A2, those stay where they are, but change signs. So 1 over the determinant times that switched around matrix. And the important thing about inverses is that the inverse multiplication is commutative. You can multiply them either way. Because they are each other's inverse, so you can multiply them in either order and get the identity matrix. So, find the inverse of the matrix, this one. Alright, so the determinant of this matrix is going to be 2 times 4 minus negative 3 times 4, which is 8, plus 12, which is 20. So then the inverse is going to be 1 over 20. And so this diagonal, we switch. So make this 4 and this 2. And this diagonal, we keep them in the same place and switch the signs. So make that a 3 and that a negative 4. And we multiply everything by 1 over 20. So 4 over 20 is 1/5. 3 over 20, negative 1/5, and 1/10. That's our inverse. And try it out. You can try it out. If you did this times 2, negative 3, 4, 4, if we multiply these together, we should get the identity matrix. So multiply this row by this column. 2 fifths plus 12 over 20, right, which would be 8 fifths, or 8 20ths, plus 12 20ths is 20 20ths, which is 1. Multiply that by the second column. 1/5 times negative 3 is negative 3 fifths. 3 20ths times 4 is 12 20ths, which is also 3 fifths, so that's going to be 0. And then do the second row by the first column. Negative 2 fifths plus 4 tenths is equal to 0. And the second row times the second column is going to be 3 fifths plus 4 tenths, which is 2 fifths, which is 1. So we end up with the identity matrix, 1, 0, 0, 1, which is what we were supposed to get if we did the inverse correctly. Find the inverses of the following matrices. You don't have to check them this time. Alright, so the determinant is going to be negative 2 times 7, which is negative 14, minus 15, which is 1 over negative 29. And then we swap these two, make that 7 and negative 2. And we switch the signs on these two, negative 3 and negative 5. So we end up with negative 7 over 29, 5 over 29, 3 over 29, 2 over 29. Ugly? Yes. But who cares? It works. Leave it as the ugly fractions and don't stress about it. 9 times 36 is 324, and 13 times 27 is 351, and so 324 minus 351 is negative 27. And then, so then we switch these two to make that 36 and that 9. And then we make these two negative, 13 and negative 27. And then we multiply by 1 over negative 27. And so that's going to be 36 over negative 27, 13 over 27, negative 27 over negative 27, I can tell you is 1, and 9 over 27. And just simplify your fractions real quick. That should be, divide by 9, 4/3. 13 over 27 doesn't simplify. That's 1. That's negative 1/3. Always simplify your fractions. Alright, use matrices to solve the system of equations. So what we can do is we can say that we make one matrix that is the coefficients. So our coefficients are 2 and 3 and 1 and negative 1. And we make a second matrix that is x and y, and then equal that to the answer matrix here. And so this is a 2 by 2, and this is a 2 by 1. Make sure that they're in the right order and that your dimensions line up. And so if you multiplied these, you would be back here. Now what we want to do is we want to solve for this. And so we are going to multiply by the inverse. So the determinant, first we need to find the inverse of this matrix. And if we multiply by this the inverse of this matrix, we make it go away. So the determinant of this matrix is going to be negative 2 minus 3, which is negative 5. So our inverse is going to be 1 over negative 5 times, switch these two, make these two negative, which is going to be 1/5, 3/5, 1/5, negative 2/5. So now what we need to do is we need to multiply this by this. 1/5, 3/5, 1/5, negative 2/5. And so if we multiply these two together, they're going to give us the identity matrix. You can check it, try multiplying them together, but that is the definition of the inverse. So if you did your inverse right, you don't really have to do the multiplication. And of course, if you multiply that identity matrix by x and y, this would just be equal to the xy matrix. But in an equation, everything that we do to one side of the equation, we have to do to the other side. I'm just going to move this over here. So this was negative 17 and 4. All right, so we also have to multiply this side. 5th, 3/5, 1/5, negative 2/5. Also have to multiply this side of the equation by the inverse. And again, double check that you're doing it in the right order. This is a 2 by 2 and this is a 2 by 1. You cannot put the inverse matrix over here and multiply them because they won't multiply. So, multiply these and that'll solve us our x and our y. So, multiply the row by the column, which is negative 17/5 plus 12/5. And then this row by the one column, that's also negative 17/5 plus negative 8/5. And so that ends up with negative 17 plus 12 is negative 5/5, which is negative 1. And negative 17 minus 8 is negative 25/5, which is negative 5. And so what we get is that x equals negative 1 and y equals negative 5. And then, to double check our work, plug those back in here. So 2 times negative 1 plus 3 times negative 5 is negative 2 plus negative 15, which is negative 17. And negative 1 minus negative 5 does indeed equal 4. So, we'll plug our answers back in and check that they're correct. And that's it. That is the end of matrices for the rest of pre-calculus. Congrats.